Hi, my name is Suresh. Today we will discuss about dimensionality reduction problem. Firstly, why do we need dimensionality reduction problem in machine learning? This is very important and a crucial stage in building machine learning models. When you have a huge features or dimensions to represent your data points, data becomes super spread out. Distance between points becomes less meaningful. Models need way more data to learn patterns reliably. This is where the issue comes. We need to reduce the dimensionality to improve the representation of the data points. So the dimensionality reduction is the process of reducing number of features in a data set while keeping the important information. It helps reduce computational time, remove noise, and prevent overfitting. Methods are mainly classified into linear and nonlinear techniques. We will discuss each of those techniques in detail. You can see two categories of dimensionality reduction models. One is linear models and non-linear models. All linear models assume that meaningful structure can be captured through linear projections. Mathematical formulations are applied under these assumptions. Linear models are one principal component analysis called PCA, two latent semantic analysis called LSA, third linear discriminant analysis called LDA. Nonlinear models are called T-distributed stochastic neighbor embedding (TSNE) and uniform manifold approximation and projection called UMAP. Nonlinear models like TSNE is useful for visualization, whereas UMAP can be used for feature extraction. I have a PhD degree with more than 15 years of industry experience, and I would like to explain more complex data science concepts in a simpler way to make it easy for learning. Please subscribe and comment for more technical videos. Let us discuss principal component analysis. It has three main steps. 1. PCA is a unsupervised linear technique that projects data onto directions of maximum variance. Second, it constructs covariance matrix and uses eigenvalue decomposition technique of covariance matrix. Third, it reduces dimensionality while preserving global variance structure without using class labels. Steps involved in PCA to perform dimensionality reduction as below. Standardize the data by subtracting mean of each feature. This will become a rectangular matrix. Second step, compute the covariance matrix. Covariance matrix is computed by multiplying a transpose of standardized matrix with the same matrix. This will give you a square matrix. Then, step 3, compute eigenvalues and eigenvectors using matrix decomposition technique. This will give you eigenvalues and eigenvectors. Step 4, sort eigenvectors and select top k eigenvectors. Step 5, project the data to top k eigenvectors, so that will become the reduced dimensions. In this example, you have data in three-dimensional space and reduce it into two-dimensional space. Step 1 finds two principal component. Step 2 projects the three-dimensional data into two-dimensional subspace. Step 3 reduces three-dimensional data into two-dimensional data. Linear discriminant analysis is another linear method for dimensionality reduction. It is a supervised approach, uses class labels in eigenvalue decomposition. Unlike PCA, it computes within class scattered matrix between class scatter matrix. This compute requires class labels, so hence this is called supervised approach. LDA is a linear method that maximizes between class scatter while minimizes within class scatter. This leads to a generalized eigenvalue problem, where eigenvectors define the direction that maximize class separation. The top eigenvectors corresponding to the largest eigenvalue are selected to form the projection matrix, which maps data into lower dimensional space with maximal class discriminability. It can produce at the topmost C-1 components, where C represents the number of classes. Let us see the comparison between principal component analysis and linear discriminant analysis. PCA is approach and LDA is approach. PCA maximizes variance whereas LDA maximizes class separability. PCA has no labels and LDA needs class labels. Principal components are orthogonal axes and linear discriminants are best class separation axis. Let us discuss how dimensionality reduction techniques are applied in text data. There are two types of dimensionality reduction techniques in text data. Latent semantic analysis called LSA, which performs similar way like principal component analysis, but it works on rectangular matrix and no covariance matrix is computed. Latent Dirichlet allocation, which is called LDA, it is a probabilistic generative model for topic modeling. Here, no term frequency and inverse document frequency representation is required. Text data contains collection of documents which are traditionally represented using term frequency and inverse document frequency called TF-IDF representation. TF-IDF represents a document by first calculating how frequently each word appears in it, called term frequency, and then scaling that value by how rare the word is across all documents, called inverse document frequency. For example, if a word has high term frequency and the same word appears across all documents, then it gets less weight. For example, stop words like a and the. Words that appear in one document but rare in the overall corpus receives high TF-IDF scores, making them more significant for the document. IDF balances this weight and it is useful for information retrieval. Given the TF-IDF representation, which is usually sparse representation, in the figure you can see terms are rows and documents are columns. Latent semantic analysis LSA performs singular value decomposition SVD to the TF-IDF matrix to reduce its dimensionality while preserving the most important patterns. LSA decomposes TF-IDF matrix into three matrices U, sigma, and V. One of them is a diagonal matrix with singular values. By keeping only the top singular values, it captures the underlying semantic structure or latent topics in the data. Words that belongs to one topic will group into one dimension. The reduced dimensions are latent topics from documents. Latent Dirichlet allocation is called LDA, is a topic modeling technique which is completely different from LSA, but it has same view of identifying topics. It uses probabilistic generative models to discover hidden themes in a collection of documents. LDA assumes that each document is a mixture of several topics and each topic is represented by a distribution of words. The number of topics are fixed ahead. It tries to estimate latent topic structure from documents with the Dirichlet priors and multinomial distribution of words in documents. This figure shows documents are mapped with the topics in a pie chart and topic word distribution on right hand side. The latent topic model uses Dirichlet priors to estimate hidden topics distribution. Let us compare LSA and LDA analysis. LSA uses linear algebra to reduce a term document matrix into continuous latent vectors. LDA is a probabilistic generative model. LSA uses TF-IDF matrix using singular value decomposition technique, and LDA estimates document topic and topic word distributions using Bayesian statistics. LSA is a less interpretable and cannot handle words with multiple meanings, while LDA handles words with multiple meanings naturally and gives clear topic structures. LSA is mainly used for semantic similarity, clustering, and dimensionality reduction, whereas LDA is used for topic modeling, document classification, and trend analysis. Overall, LSA focuses on abstract latent features, while LDA focuses on discovering explicit interpretable topics in a corpus. LDA requires huge data to estimate those distributions, and it will be noisy topics under small data. We can discuss two popular nonlinear dimensionality reduction techniques, T-distributed stochastic neighbor embedding (TSNE) and uniform manifold approximation and projection (UMAP). They are nonlinear dimensionality reduction techniques. They are used to visualize high-dimensional data in 2D or 3D. TSNE focuses on preserving local neighborhoods by converting high-dimensional distances into probabilities, making it excellent for separating clusters, but sometimes distorting global structure. UMAP preserves both local and global structure by modeling the data manifold using graph theory and topology, often producing faster and more stable embeddings than TSNE. TSNE can be computationally intensive and sensitive to hyperparameters, while UMAP scales better to large datasets and retains more of the overall data geometry. Summary: TSNE is excellent for visualizing distinct clusters locally. UMAP preserves global structure and scales to large datasets. Conclusions and key takeaways. We have discussed overview of dimensionality reduction techniques. This includes linear techniques, which are PCA and LDA. For text data, we have discussed LSA and latent Dirichlet allocation. We have also discussed nonlinear techniques such as TSNE and UMAP.